Okay. So, what have we done so far? We've talked about metrics. We've defined S1 with the arc length as a metric. And last lecture, we finished classifying all the isometries of S1, right? So they're rotations and reflections. Okay, so that's where we stand. What I want to do now is, well, first of all, actually prove that Rn with the Euclidean distance is a metric, so we haven't done that yet. The reason we haven't done it is because the key point in that proof I wanted to save until we were ready to sort of actually use it for some, I mean, we're going to generalize that idea and do something more interesting with it. All right, so that's why we were waiting on that. So I'll do that first, and then we're going to discuss, well, we're just sort of going to explore the idea of trying to put different metrics on Rn. How can we come up with more metrics than just, well, there's D2, which, okay, so D2 is the usual Euclidean distance. So D2 of xy is the sum over I, xi minus yi squared, square rooted. Okay, so that's the usual Euclidean distance. So there's a 2 there because there's squares and a square root. There's a bunch of other metrics on Rn. So there's a D1 and a D infinity, which is already in the notes. I'm not going to prove those are metrics. That's actually much easier than proving D2 is a metric, and I'm leaving it as an exercise for you. So we're going to first of all prove this is a metric, as I said, and then we're going to see if we can just play with this a little to get other metrics. Okay. And that will naturally lead into a discussion of a kind of space that is genuinely radically different from Rn, which is Minkowski space, which is the basis for special relativity. So that will be next lecture. Okay, so let's prove that this is a metric space. All right, so we've got to check 4 things. 3 of them are just easy, right? So I'm not even going to write them out. So M1, well, the first formula there, I mean, it's that thing inside the brackets better be non-negative, otherwise the square root doesn't make any sense. So certainly we get something non-negative. This we know by basic real analysis is true, right? If that sum of squares was 0, all the things would have to be 0, which means xi equals yi. And it's clearly symmetric because minus 1 squared is 1. Okay, so M1 through M3 is clear. So the only thing to prove is the triangle inequality. Okay. So for that, we're going to first study an inequality called the, well, in this special case, it's called the Cauchy inequality. So claim, if I have real numbers R1 up to Rn and S1 up to Sn, then am I getting this right? Okay, so let's prove this first. So proof of the inequality. And there's sort of a clever trick here, which then becomes manifest more generally in what's called the Cauchy-Schwarz inequality for inner products. And the trick is to just get this inequality as the discriminant of some polynomial function. All right, so that means we introduce a new variable, lambda, and we define f of lambda to be the sum over I, Ri plus lambda Si squared. Okay, so now we're thinking of this sequence of R's and S's as fixed, and lambda is varying. Okay, so that's clearly a polynomial function in lambda with some coefficients. Well, it's a sum of squares, so it's non-negative. And if you, in lambda, it's quadratic, right? The highest power of lambda that appears is a square. Okay, so what do you know about a quadratic function with real coefficients which is never negative? Well, its discriminant has to be greater than or equal to 0, right? Sorry, less than or equal to 0, right? Because if it was greater than or equal to 0, it would look like this. Okay, it's possible that the discriminant is negative. That would just mean that that quantity is never 0. That's okay. We're not talking about complex roots or anything. But if, so let delta be the discriminant. We'll write down the formula for it in a second. So we know from the quadratic formula that if the discriminant was strictly positive, then we could write f as a product of two linear factors, distinct linear factors. So it would look something like this. But that would mean that if we took the point halfway in between, I mean, it doesn't necessarily, I mean, it could be shifted, right? It doesn't have to be at the origin. But if we took the value in between those two roots, the value of f would be negative, but it's never negative. Okay. So since f is never negative, the discriminant must be less than or equal to 0. But if we think about what the discriminant is, okay, so the discriminant is b squared minus 4ac, right? So if I expand that out, that's the sum over I, si squared lambda squared plus 2ri si lambda plus ri squared. Okay, so if I accumulate in the usual sort of notation for a, b, and c in a quadratic, so a will be sum over I si squared, b will be sum over I 2ri si, and c will be sum over I ri squared. Okay, so the discriminant is, we'll take the 2 out the front, so b squared will be 4 sum over I ri si squared minus 4ac, so that's 4 sum over I ri squared sum over I si squared. Okay, so to say the discriminant is non-negative is precisely to say that that product is less than or equal to the square of that sum. Right, so we've got the inequality in the claim. Right, so that was just a little bit of real analysis. Okay, so what has that got to do with the triangle inequality? Well, it's directly implies the triangle inequality. So to prove M4, we have to show that d2xy plus d2yz is greater than or equal to d2xz. Well, just to write that out, so that's the sum over xi minus yi squared, square rooted greater than or equal to Okay, so the trick here is we're going to just write this as AI, this as BI, and then that's AI plus BI, and then we just apply this inequality and we're done. Okay, so set AI equals equals xi minus yi, b equals y minus zi. Then okay, so that's the thing which is inside, right? AI plus bi is xi minus zi, if that's readable. So what I've just written is the stuff inside the square root over there. Okay, so expanding that out. Well, now I use this inequality. Well, I square root both sides. Okay, so this is less than or equal to right. Why is that? Well, just only pay attention to part of that expression. Right, so if you square root both sides of that equation, so they're both positive quantities, right? The sum of squares on the left are positive, and then I've got this sum on the right, and I've squared it, so it's positive square root both sides. That's order preserving. So I get that the sum of I ri squared square root times the sum of I si squared square root is greater than or equal to, well, the term that I have here. But, well, I mean, maybe it's worth spelling out that there's actually an absolute value that's gone missing there, I suppose. Right, so this is Cauchy, but what Cauchy actually says is this is square rooting gives me the square root of the square, which is the absolute value, right? But the absolute value is greater than or equal to the thing itself. That's what I'm plugging in. Okay. All right. But that is this. Right? That's just expanding that out. Okay, so what have I shown? Well, this last line is literally this quantity here. And I've shown that it is greater than or equal to this quantity here. So we're done. Okay. Any questions about the proof? Okay, so the thing to notice here is that the proof of the triangle inequality hinged on some claim, sort of subclaim. And this subclaim is something we'll come back to in a more general context. All right, so the next exercise asks you to check the metric axioms for D1 and D infinity, as I said. Okay, so we've got Rn with Euclidean distance as a metric space. Now what we want to do is see if we can bootstrap off this basic fact to get even more examples of metrics. By the way, it's probably worth me remarking that some proofs are meant to be obvious, like, yeah, you should, if you're thinking clearly, just have seen how to do that. Other proofs involve tricks which seem kind of clever. This is an example of a clever trick. Right? So once you've seen it, you should notice A, well, that was clever. B, I should remember that because maybe that'll be useful. Right? So this is a good trick. Okay, so we're going to, so I'll leave the following as an exercise. It's not difficult, and we're going to use it. Okay, so if I've got a metric space and a bijection, well, if you have a bijection between two sets, I mean, you're just renaming the elements, so to speak, right? So if I have a metric that tells me the distance between points in X, and Y is basically the same set as X, well, then I get a metric on Y. That's clear, right? I just make the distance between points in Y the distance I would measure between them if I was thinking about them as points in X. That is, I would define the metric dy y1, y2 to be the distance between row y1 and row y2. Okay, so check that that's a metric, that's an exercise. Well, what's the point of giving you that exercise? The point is, if I know a metric space, say Rn D2, and I know a bijection from, say, Rn to itself, then I can induce a new metric. Right? So we're going to play that game and see if we can get anything new. Okay, so a fix B invert, yeah. So take an n by n invertible matrix. Here's a new function of a pair of points in Rn. There's the formula. Okay, first I have to justify that quantity inside the brackets is actually non-negative, so that that is well defined, but that'll come out of what I'm about to do. And I claim that formula for any invertible matrix B gives me a metric. Well, that's just an immediate consequence of the exercise. Right, because let rho be the bijection from Rn to itself, which is given by multiplying by this matrix. Potentially, I should call that d rho instead of dy, because it's actually determined by rho. Also, this exercise then says that I've got a bijection. If I take the d2 metric on Rn, I get a new metric on Rn. So what is it? So it's the metric which takes a pair of points x, y. By definition, it declares the distance between them to be the Euclidean distance between the result of applying rho to x and rho to y. That's just b times x and b times y. And we know how to write the Euclidean distance in terms of matrix multiplications. In particular, that quantity inside the brackets is non-negative. And just manipulating that a little, we'll obtain the formula in the statement of the lemma. Right, so continuing that calculation, so, well, that is b times x minus y, all transpose times b times x minus y, which, taking the transposes, is okay, so that's the formula we had. All right, so that's a metric. Okay, so now the question is, is that actually a new example? What kind of metric is that? So let's take the most, but perhaps the simplest example. I'll take in positive real numbers. Then the matrix, which is diagonal, it's clearly just the square of that diagonal matrix. That diagonal matrix is symmetric, so I can think of that, if I call this B, that is BT times B. All right? So in particular, the lemma says that the following is an example of a metric. The distance from x to y is the square root of the sum of lambda I times xi minus yi squared, square root. So this is a metric. Right, as long as I fix a sequence of positive real numbers, this formula is just what you get by plugging in that particular diagonal matrix, right, if you think about it. So this is a metric on Rn. So you're just sort of stretching the axes. If it's, if lambda I is less than 1, then what are you doing? So if lambda I is less than 1, it corresponds to stretching your measuring stick, right, so that you assign a smaller distance to a fixed interval. And vice versa, if lambda I is greater than 1, then you're shrinking your measuring stick. Okay, so that's a new example of a metric. Okay, so now the game we're going to play is to look at that formula and wonder, well, does this work more generally? So can we stick, what kind of matrices P can we stick in the place of BTB and still get a metric? Okay, so given a matrix, let's define a function on pairs of points in Rn to be given by this formula. Okay, so that's a natural generalization of what we just discussed. So for which p's does that give a metric? Well, what's the first problem that we have to deal with? So these four axioms impose, in principle, four constraints on the set of matrices. So actually, once we've dealt with M1 through M3, M4 is basically automatic, as we'll see. So let's deal with M1 first. Well, the way we've set it up I mean, if this even makes sense, it's got to be non-negative, right? Because it's a square root. But the issue is that quantity inside the brackets even non-negative to start with, right? Okay, so that's the first thing we'd need in order for that to even be well defined. Okay, so for that to be well defined, we would need for all, let's say z, right, so for that expression to be well defined for all x and y, I'd need this thing inside the brackets to be non-negative. I mean, it's a number, but it doesn't have to be non-negative for an arbitrary p. I'd need that expression to be non-negative for all x and y. But as x and y range over all vectors, clearly by taking y to be 0, I can get that vector to range over all possible vectors. So this is the same condition with a z. Okay, so that's condition 1 that I'd need for that to even get started. And this is called positivity of p, for the obvious reason. Okay, so if I had this for all z, then at least that formula would be a number. So this would be a well-defined function of x and y. And then I can start to ask, does it satisfy these axioms? Well, the first axiom is automatic because of the way I've set things up. It's a square root. The second is not automatic, though. Right? So what would the second axiom say? So I'd need to have this quantity, 0, if and only if x equals y. Well, it's a square root, so that's the same to say the quantity inside is 0 if and only if x equals y, which is the same as to say that ztpz is 0 if and only if z is the 0 vector. Okay, so this is called definite. If a matrix satisfies this, you say it's definite. Right, so if we had those two properties, M1 and M2 would be satisfied. Okay, M3 is easy, right? Have a look at the formula. If I swap the order of x and y, well, that just corresponds to multiplying that factor by -1 and that factor also by -1, and everything's linear, so they cancel out. Okay, so M3 doesn't impose any condition at all. Okay, so that only leaves M4. All right. So basically what I'm now going to say is that as long as P satisfies these two conditions, M4 is also true, so that that's a metric. Almost. Okay, so there's a little bit of a wrinkle, which is just that I can assume without loss of generality that the matrix P is symmetric, you see. Right, so given a P, set P symmetric to be a half P plus P transpose. Well, we agree that's a symmetric matrix. I claim that the candidate metric, that is this function of two vectors that I get out of P, is the same as the function I get out of the symmetrization of P. Right. And for that reason, who cares about non-symmetric matrices, right? We're interested in the metric at the end, so I might as well only care about symmetric matrices. So that's the point of the claim. Let's just check. Right, so, well. It's just a calculation. If you just plug it in, you'll see that you get the same thing. So maybe I'll just skip it. It's in the notes anyway. Okay, so we may restrict to symmetric P without loss of generality. All right. So I think you've all, well, have you guys seen orthogonal symmetric matrices and this kind of business in the linear algebra class? Yeah. So at least the notions of symmetric matrix, and I mean the linear algebra of what I'm about to tell you, I assume is familiar to most of you. All right, but maybe this is appearing in a new context. Okay, so the following definition you may have seen before. So definition: a matrix P is called positive definite if 1, P is symmetric, okay, and as I just explained, the reason why we don't care about non-symmetric matrices is because we can just symmetrize and then we get a symmetric matrix. 2, it needs to satisfy these, or the first of those conditions. And 3, okay, the second condition there. Right, so that's a positive definite matrix. Now, the lemma is that as long as P is positive definite, this function is another example of a metric on Rn. Any questions so far? And the proof is just going to parallel what we did for D2 on R2, on Rn. And the key is basically the same inequality, just reappearing again. All right. Okay, so note. Okay, so for the duration of the proof, I'm going to use these angled brackets to stand for this quantity, VTPW. And if P is symmetric, then you observe this pairing is symmetric, just because if you transpose, think about a number as a 1-by-1 matrix. You take the transpose, it's still the same 1-by-1 matrix. So this is a number, that is, it's a 1-by-1 matrix. Take its transpose, you'll get WT PTV. Well, if PT is P, that's WT PV, which is just this pairing. Okay, so if the matrix is symmetric, then that pairing is symmetric, and that's what we're going to use in the proof. All right, so lemma P is a metric if P is positive definite. And that's as much as you could possibly hope for, right? Positive definite is necessary, and we're saying it's also sufficient. Okay. So again, this proof hinges on a claim, which is some inequality that looks just like the one I had before. Later, when we get to inner product spaces, we'll prove this in general. This is sort of the baby version of what's called the Cauchy-Schwarz inequality. Throughout everything I'm going to say now, P is positive definite. Okay, so here's the statement. Okay, so we've got our fixed positive definite matrix P. We take two vectors V and W, and then claim, I mean, these are both real numbers. I mean, in the full Cauchy Schwarz, we have to worry about complex numbers, so there's absolute values around, but at the moment we're talking entirely about real numbers, and we just claim this inequality. And once we've seen the trick from the previous proof, this seems fairly straightforward. Okay, so we're trying to prove this for a fixed pair V and W, right? So let's observe that for any lambda, so V and W are fixed, and any lambda, the following calculation works. Okay, well, why is that true? Yeah, right. Because that expression there, if you think about it, so if I take x comma x p, that's xt px, and by the fact that p is positive, that's greater than or equal to 0. Okay, so here we're using, if you like, condition 1 on p. Right. Now I'm going to use that this expression here is linear in both variables. If I put a linear combination for v or w, I get a linear combination out, and that's simply because the transpose and multiplication of matrices is linear. Right, so I can just expand this. Okay, so that was just linearity, nothing else happened. Now, I can collect the middle two terms because the pairing is symmetric. Right? The pairing is symmetric. I just erased it. The reason for that was because I assumed that P was symmetric. Oh, sorry. I wrote the wrong number, didn't I? That's actually property 2 in our definition. Now I use that P is symmetric. That means the pairing is symmetric. So that's this. Right, so now is the magic trick. I mean, observe, we fixed V and W, and this is true for all lambda, right? So I get to pick lambda, and it's still true. So we just use lambda to be this number. Okay, the pairing of V with W divided by the pairing of W with W. Again, we use the fact, well, this is the first time we've used it, I guess. We use number 3 to see that it actually is a number. That is, we're not dividing by 0. Well, strictly speaking, I don't know that's non-zero. I mean, W could be 0, right? I said V and W are anything. If W is 0, of course, the pairing of itself with 0, right? Look at this expression. But who cares about W being 0? Because this is obviously true if W is 0, right? If W is 0, that's 0. The right-hand side is 0. Okay, so the number is true. So I may assume W is non-zero, otherwise the lemma is trivial. And as long as W is non-zero, then by condition 3, that lambda is well defined. And what does this inequality say in that particular case? Well, that's 2VW squared divided by WW. And lambda squared times this will give me plus VW squared on WW. Right? So I told you it was magic. So we're done. I mean, I'll write the last line, but that's it. Let's now just rearrange that, and we've got our inequality. Right, so that says 0 is less than or equal to VV P minus VW squared P. Well, I suppose there is I need to use that it's positive when I multiply through by it, I suppose. It's worth being aware of that, right? So we can multiply through and find, and then rearrange. Okay. So that's it. And you'll recognize that, in the case where P is the identity, this is simply the same inequality that I had before. Right? Okay, so let's use that to prove the lemma. Okay, so proof of lemma. Okay, so we need to show again dpxy plus dpyz is greater than or equal to dpxz. As before, so basically it's the same calculation. Right, so this is one side of the inequality I'm trying to show, right? This sum of square roots is by definition dpxy plus dpyz. And then just expanding that out. So I've got this. Now I just invoke the claim. Square rooted. Right, so the claim goes inside the square root. Okay, but if I square and square root, that's the absolute value. And then that's greater than or equal to just the value itself. As a 2. Which by linearity is just a plus b. A plus b. Okay, so then square rooting both sides gives me the triangle inequality for dp. Okay, so we have now induced from every positive definite matrix a metric on Rn. EP for us seems like we have lots of new metrics, right? Well, not really. Okay, so we end the lecture on a bit of a downer. So exercise. Okay, so prove, so what have I done? I've taken a positive definite matrix and I've given a metric, right? Well, take two positive definite matrices. You could ask, when do they give the same metric, right? We saw an example of that where I took a matrix and its symmetrization, they gave the same metric. So of course it's possible that you would get two matrices inducing essentially the same metric, and by essentially the same I mean isometric metrics, if you get my meaning. So let's prove that so what's the so take two positive definite matrices P and Py and P1 and P2. The appropriate notion from linear algebra of when two positive definite matrices sort of count as the same is if they are related by a change of basis. The appropriate kind of change of basis is an orthogonal matrix. Right? Orthogonal just means QTQ is 1. Okay, so this is the appropriate notion of when two positive definite matrices are essentially the same in linear algebra. And you can check that if they're essentially the same in this sense, then they give rise to essentially the same metric spaces. That is, there's a bijection from Rn to itself, which is distance preserving, where you use distance P1 on the left and distance P2 on the right. This is what you mean by two metric spaces being the same. Right? Up to a reordering of the points, they measure the same distances. Okay, so if two positive definite matrices are related by this Q, then they give essentially the same metric up to an isometry. Well, every real symmetric matrix is equivalent in this sense to a diagonal matrix with positive numbers on the diagonal. So in this case, let's say P1 is equivalent to P2, right? If such a Q exists. Okay, so if you remember your linear algebra, every P is equivalent in that sense to a diagonal matrix. These are the eigenvalues, which are positive. But the metric which I associate by this construction to a diagonal matrix, I mean a diagonal matrix with positive elements on the diagonal is a positive definite matrix. And the metric I construct from such an example, the dp, is exactly the metric that I wrote down earlier. Okay, so this P, in a sense, is not interesting. It just gives us back this scaling, which was the most obvious way of sort of changing D2, the normal Euclidean metric. So that makes this matrix not very interesting, but then, well, no positive definite matrix seems very interesting because they're all giving metric spaces which are isometric to Rn with this metric. Okay, so what was the point of the whole lecture then if we don't get any new examples of metrics? Well, we may not have gotten new examples of metric spaces, but we found a new way of thinking about the old examples, right? The usual metric and also this metric. We figured out how to view them as coming from a particular class of matrices, namely positive definite matrices. But positive definite matrices sit inside a larger space of matrices. And if we apply the same kinds of ideas to those matrices, we end up with a new class of geometries. Within that new class of geometries are very interesting examples, such as Minkowski space, which we'll talk about next lecture. Okay, so this was our way into the idea which generates those examples.